Hello everyone. So far in this week we have looked into seismic design and ductile detailing of masonry buildings. We have looked into their material specifications, wall geometry, lateral supports as well as ductile detailing related to provision of reinforcement. Today in this class we will initiate a design example problem to illustrate seismic design of masonry buildings. Here we shall be designing a multi-purpose masonry building with plan and elevation details as shown over here. The building is to be constructed at a medium soil site located in New Delhi. The live load on first and the roof level are 3 kN per square meter and 1.5 kN per square meter respectively. We need to design this southern wall along with ductile detailing for seismic resistance. We also have other geometrical parameters given to us such as the thickness of slabs and walls. The slabs are 125 mm thick and the walls are given to be 250 mm thick. In this case we are giving the thickness of only the external walls. The internal walls are not shown over here as of now. Then we have openings in these external walls in terms of windows and doors. While doors have a height of 2.1 meters, the width of the door is 1.2 meters. The windows have dimension of 1.5 meters width and 1.2 meters height. And here you can see we have two doors, one in southern wall and another in northern wall, and we have total number of 8 windows, one each in northern and southern walls and 3 each in eastern and western walls. We shall be using class 10 brick as our masonry unit for constructing our building. We shall also be utilizing mortar of grade M1. We will see what are the different properties. We have already looked into different properties and we shall also look as we illustrate through this example. The masonry can be assumed to have a unit weight of 20 kN per meter cube. At the same time, reinforced concrete and steel reinforcement have unit weight of 25 kN per meter cube and 78.5 kN per meter cube. The reinforcement has a grade of Fe 500. We shall also use concrete which is of grade M20 as we shall mention later. Now this is the wall which we want to design. Particularly we shall be designing the wall in the lower story so that it takes care of higher load coming from upper stories as well. Okay, so let us get into the problem. The first thing which we want to do is to estimate what would be the design seismic load. Now as you must be aware by now that IS 1893 2025 version has been withdrawn. So we shall be following IS 1893 2016 version. We shall look about more procedural as well as example based on IS 1893 2016 version in the upcoming weeks, possibly in week 11, because earlier we have dedicated our time in looking into estimation of design seismic load based on IS 1893 2025 version, which is now withdrawn. So we shall look into that as well, but here we shall summarize the design steps using this illustrative example which you need to follow. We will look into the procedure separately. The first step in calculating or estimating design seismic load is to estimate seismic weight of the building. Now we shall calculate the seismic weight of different floors differently. So for first floor level we have the self weight of slab calculated as shown over here. The slab is 125 mm thick, has dimensions of 8 meters by 12 meters in plan. The unit weight of concrete is 25 kN per meter cube, giving a self weight of slab as 300 kN. The self weight of walls in this case is obtained as we have considered the wall coming from both the stories, that is half from below and half from above. So, we have considered the wall perimeter as 8 plus 12 into 2, and this is the height, that is 3 meters. From this we have removed the openings. We have considered openings to be half on either side. So, that is how we have done this calculation. Please take your time to understand how this has been done. Then 0.250 represents the wall thickness in meters, and 20 is the unit weight of masonry in kilonewton per meter cube, thus giving us the self weight of walls as 502.8 kilonewton. Now, based on this, we have the total dead load at the first floor level as 802.8 kilonewton. At this point, I would like to reiterate that since this is a masonry building, it has RC slab spanning into the masonry walls. So, there is no concept of beams and columns in this case. Whenever the dimension of masonry wall is such that the width or the length of the wall is less than 4 times of its thickness, then we will call it a masonry column, but that is not the column or the RC column which we used to talk in case of RC framed building. So, that is how in this case, while calculating seismic weight, we do not need any beam because there is no beam as such. Then the live load at the first floor level is calculated. The live load intensity was given as 3 kilonewton per square meter, and the planned dimensions are 8 meters by 12 meters. Then we have 25% of live load contributing to seismic weight as per table 10 of IS 1893. So, this live load is estimated to be 72 kilonewton contributing to seismic weight, and therefore, the seismic weight at the first floor level is equal to 874.8 kilonewton. Then we shall calculate the seismic weight at the roof floor level. How shall we calculate that? We shall calculate it again in a very similar manner. This time the self weight of the slab remains the same, but the self weight of walls is reduced to half. Why half? Because we are ignoring presence of any parapet wall. So, the tributary area of walls which contribute to the seismic weight at the roof level is only half in this case from the bottom. So, the total dead load at the first floor level now becomes equal to 551.4 kilonewton, and based on this clause 7.3.2 of IS 1893 part 1 2016, we ignore the contribution of live load at the roof level. Why do we ignore the contribution of live load to the seismic weight at the roof level? Because earthquake is a rare occurrence, and we assume that during the earthquake there was no live load at the roof level. So, now the seismic weight at the roof level is calculated, which is 551.4 kilonewton. So, the total seismic weight of the building actually is equal to 1426.2 kilonewton. So, here we have added the seismic weight of the first floor and the roof level. So, once we have the seismic weight known to us, we shall obtain the dynamic properties of the building. What are the dynamic properties of the building? Essentially the natural period, if we are following equivalent static method to obtain the design seismic load. So, in this case, based on IS 1893 part 1 2016, for a masonry building, the expression for fundamental natural period shall be T equals 0.09 h divided by square root of d. Here h is the height of building from the base level. Here every story is 3 meters high. So, the total height of the building from base is 6 meters. D is the base dimension of the building at the plinth level along the considered direction of earthquake shaking. Now, since we are designing the southern wall, we are interested in earthquake shaking happening along the east-west direction. So, the value of D is equal to 8 meters. So, based on these, we have calculated the fundamental natural period of the building as 0.191 seconds. Then based on this natural period, the design acceleration coefficient considering medium soil site is equal to 2.5. This is again based on clause 6.4.2 of IS 1893. So once we have this value of SA by G, we also need some other parameters which are zone factor, importance factor and response reduction factor. Now seismic zone factor actually depends on the location of the site. Since our site is located in New Delhi, which is located in seismic zone 4, the value of zone factor is equal to 0.24. Here I have given different tables and figure references for different factors, so you can look into the same. Then for multi-purpose building, as in our case, the importance factor is equal to 1. Then the response reduction factor is found to be 2.5. How do you find this value, response reduction factor? What does it signify? It signifies that since we are designing our building to be behaving in an inelastic manner, we believe that we shall be designing it for a force which is 2.5 times lesser than the design force for the elastic case. And for a building comprising of unreinforced masonry with horizontal RC seismic bands and vertical reinforcement at corners of rooms and jambs of openings with reinforcement as per IS 4326. For such building, the value of response reduction factor shall be 2.5. Here I would like to reiterate that IS 1905 deals with structural use of masonry related to design, while IS 4326 is the code for earthquake resistant design of buildings. So the section 8 of IS 4326 gives you ductile detailing related to masonry buildings. As of now, we do not have a separate code for ductile detailing of masonry buildings. So this very factor, response reduction factor, has been told as force reduction factor or behavioral factor in different codes. So you need to understand that all of these names are actually more or less identical. So this very factor takes into care of over strength and ductility. So now we have all these factors known to us. We will estimate the design seismic load or the design base shear as VB equals AH into W, which is equal to Z by 2 times of SA by G times of W divided by R by I. Upon substituting all the values, we get the value of VB as 171.14 kilonewton. Now based on a clause 7.2.1 of IS 1893 part 1 2016, where we specify the minimum design base shear for any zone. In that case, we are given that the minimum design base shear should be 1.6% of the seismic weight. So 1.6% of seismic weight is 22.82 kilonewton. So our estimated design base shear is much higher than that, so it is all right. So our design base shear on the building shall be 171.14 kilonewton. Now we shall distribute this design base shear into different floors. So that distribution is done using this very simple expression, Q equals WH square divided by sum of WH square for different floors and then multiplied with the design base shear. So from here we calculate it to be equal to 48.6 kilonewton at the first floor level and 122.5 kilonewton at the roof level. The same is shown over here as a schematic diagram. Now this design seismic force on various floors is used to obtain the design story shear. How do we obtain the story shear? For the top story, the story shear shall be equal to this very force 122.54 kilonewton. At the bottom story, it is obtained as the sum of all the forces that is being applied above it. So that shall be 122.54 plus 48.60 kilonewton, which gives us 171.14 kilonewton. For a quick check, what you can do is that design story shear for the bottom story shall always be equal to the total design base shear, which was 171.14 kilonewton. Now, once we have this story shear known to us, we will notice that in our case, for earthquake loading along east-west direction, we have two walls. One is the northern external wall and another is our southern external wall. Both of those walls actually resist the earthquake loading. So, how will you consider it? In our case, we were fortunate that these two walls are identical in terms of material as well as geometry, and therefore they have very similar stiffness, and that is how we can tell that each of them will attract equal story shear, which is 85.57 kilonewton. Now, at this point I would like to reiterate that this is true for buildings with rigid diaphragm action. So, it means that we need to ensure that the RC slab of this building is spanning completely over the masonry walls. If it is not spanning completely, it must be anchored properly, but if it is not the case, then the slab will not be able to provide you rigid diaphragm action, and if the slab provides you flexible diaphragm action, then you need to distribute this story shear in proportion to the tributary area. Again, in this case the tributary area will also be similar. So, you shall be again getting the same value of 85.57 kilonewton. But what happens if you have the rigid diaphragm action, but your walls are not identical? Then in that case you need to distribute them in proportion to the stiffness. So, you need to calculate the stiffness of the wall or the rigidity of the wall. We will go through the procedure to estimate the rigidity of this wall. We will actually calculate the rigidity of this southern wall as an example. Now, however, it is not required in our case. So, for a fixed wall, which means that the fixity is at bottom as well as top, in that case the rigidity or stiffness of a solid wall without opening is given by Et divided by h by d whole cube plus 3 into h by d. Here E is the modulus of elasticity of masonry, T is the thickness of the wall, h and d are height and the other dimension or the length of the wall as shown over here. Then we can also have the cantilever wall, in which the bottom will be fixed but the top will not be fixed, which means that it is a freestanding wall, very similar to a compound wall or a retaining wall. So, in those cases the stiffness will be much lower and it shall be obtained as Et divided by 4 times of h by d cube plus 3 times of h by d. So, there is a factor of 4 over here in this weight term, as you can see, which actually reduces the value of stiffness or rigidity in case of cantilever walls. Now, we shall not be going into the depth of derivation of these expressions. You can refer to any textbook on design of masonry buildings or design of masonry systems. There you shall be able to find the source of these expressions. Now, in this case the modulus of elasticity of masonry E can be found as EM equals 550 FM. I would like to say that EM and E are the same in this case. So, the modulus of elasticity of masonry is obtained empirically by multiplying the compressive strength of masonry with 550. Now, the compressive strength of masonry FM is again found to be 0.6 times of FB raised to the power 0.5 times of FMO raised to the power of 0.3. Here FB and FMO are the compressive strength of brick and mortar respectively. So, since we have used a class 10 brick in our case, which as per IS 1077 gives us the compressive strength as 10 megapascal, this is the minimum compressive strength of class 10 brick. You can have higher value as well, but if you have a value of exceeding 12 megapascal, then you shall classify it as class 12. So that's how we are assuming FB as 10 megapascal, and the motor which we have used is of grade M1. So which as per IS 4326 has a minimum compressive strength of 5 megapascal. So after substituting these values, we get the value of modulus of elasticity of masonry as 1691.24 megapascal. Now at this point we shall not be utilizing this very value for finding out the rigidity of our wall, because we shall express it in terms of ET. Why we shall express it in terms of ET? Because modulus of elasticity of the wall remains essentially constant, because we are not changing the material within the same wall. Also the thickness is not changing. So we shall find this out in terms of ET. Now let us get into the example illustrating how do we obtain the stiffness or rigidity of our wall. So this is the elevation detail of our wall which we want to find. This is the southern wall in the ground story. So for finding the rigidity of this wall or the stiffness of this wall, we shall find out what shall be the flexibility of this wall, or what shall be the value of lateral translation of the top with respect to the ground when we give a lateral force of 1 or unit at the top. So in order to find delta wall, we shall write this very expression. How we have obtained this expression? Delta wall is expressed as delta solid wall fixed case. We assume that first of all there will be a solid wall without any opening and fixity at the top. Obviously in our case also the delta wall, this is also a fixed wall. Why? Because of the presence of RC slab spanning over the wall completely. So in this case, first thing which we have assumed is to be solid wall. So we have ignored these openings. Now I would like to say that in such cases, if you have two walls adjacent to each other, then both of them will have the similar value of deflection, but they will add their stiffness. So the effective stiffness will be the sum of the stiffness of both the walls. But if you have two walls placed one above the other, then the stiffness of the two walls will not be added together to find out the effective stiffness. Instead, the deflection of the two walls shall be added together to find out the total deflection at the top. So what we are doing now is that from this solid wall we are removing this strip A. Strip A is this very strip where I have highlighted it using vertical dashed lines throughout. So this is the strip A. Again this is a solid strip. So we are removing this strip A. So we will be left with wall portion 5 only, and then we are adding the wall portions 1, 2, 3 and 4. 1 is this very portion, 2 is the portion between door and window like this, 3 is the portion between window and the end of the wall, and 4 is this very portion, the long portion over here. So that's how we have written this very expression, because delta of the wall we have divided into various components. One is your solid wall, we have removed the strip A, and then we have added this very system of delta 1, 2, 3, 4. This system we are taking it as 1. So delta 1, 2, 3, 4 actually considers the openings as well. So here we have tried to find out the expressions for various terms, like delta of solid wall shall be found as 1 over the rigidity of solid wall. In the fixed case we already have the expression, so we have substituted those values. For the solid wall, the value of H shall be 3 meters and value of D shall be 8 meters. After substituting, we get the value of delta as 1.178 upon ET. Then for delta strip A, this is also fixed case because there is a wall above that. So, this is also fixed case. Again we have substituted these values. What is the value of H in this case? The height of a strip A is 2.1 meters. It is up to the top of the door and window. If you recall from last lectures, we have also mentioned that the top of all the openings should be tried to keep at the identical level, so that we can provide a lintel beam throughout. Okay. Then upon substituting these values, we get the value as 0.806 upon ET for delta strip A. For finding delta 1, 2, 3, 4, it is little bit more complicated. First of all, it will be the inverse of the rigidity of 1, 2, 3, 4 system. Now, if you observe, the system 2, 3, 4 is in parallel with system 1, which means the rigidity of system 1, 2, 3, 4 will be the sum of rigidity of system 1 and system 2, 3, 4 taken together. So, that is what we have written over here. And again for the system 2, 3, 4, since system 2 and 3 taken together are in series with system 4. So, the value of rigidity shall be obtained over here. You can try doing this on your own, take your time. If you are not able to get how do we get to this, you can look into other reference books as well, or you can pose questions as well onto this. Then after doing this, again this very factor R 2, 3, that is stiffness of the system 2, 3 taken together, these two are in parallel. So, this shall be equal to the sum of rigidity of system 2 and rigidity of system 3. So, that is how we have found out this very expression, and again all of these are fixed in nature, because these are surrounded by or superseded by another wall segment at the top as well and the bottom as well. So, after substituting these values for H and D for respective walls, we obtain the value of delta 1, 2, 3, 4 as 1.29 upon ET. So, you can take your time, you can pause the video and look into these calculations. You can try doing on your own as well, so that you get more confident with these calculations. And once we get these very three values, delta solid wall, delta strip A and delta 1, 2, 3, 4, we substitute it in our initial expression and we get the value of delta wall as 1.662 upon ET. So, the value of a stiffness of wall or the rigidity of wall shall be reciprocal of this and shall be equal to 0.602 ET. So, this is how you estimate or calculate the stiffness or rigidity of the wall. Now, if your northern and southern walls would have been different, you would have got different values of rigidity of these walls, and in that case the design shear force or the story shear force for this ground story would have been distributed among these two walls in proportion to their stiffness. Okay. Now, let us also calculate what is the vertical load at the wall base. We will need this very vertical load at the wall base while designing our wall. So, in this case the self weight of the slab, since we are considering at the wall base, it shall be from both the stories or both the floors. So, it shall be 2 times of 125 millimeter thick slabs. Then we are taking only the tributary area for our wall, that is a southern wall. For southern wall, the tributary area will be a triangle, half into 8 into 4. You can pause the video, try doing on your own, so that you get more confident with this. Then 25 kilonewton per meter cube is the unit weight of reinforced concrete. So, this way we get the self weight of slab as 100 kilonewton. The self weight of walls up to 2 floors, which we calculate it to be 196.8 kilonewton. A very detailed way we have shown it over here, so that you can easily understand it. So, what we have done is that we have taken the dimension of the wall in one floor 8 into 3, and then we have removed the openings, and then we have multiplied it with 2 for 2 floors, and that is how we have obtained the cell weight of walls. So, the total dead load at the wall base has been found to be 296.8 kilonewton. The live load at the wall base is also found out using live load at both the floor levels. At the first floor level, the live load intensity was 3 kilonewton per meter square, and at the roof level the live load intensity was 1.5 kilonewton per meter square. Then we have the tributary area, very similar to the case of cell weight of slabs. So, this is calculated as 72 kilonewton. Here you will realize that we have not ignored the live load at the roof level. Why? Because we need to ignore live load, because we can ignore the live load contribution to the seismic weight, but for calculating vertical load we cannot ignore the live load. So, summing these two, we get the total vertical load at the wall base to be equal to 368.8 kilonewton. So, in this class we have estimated the design seismic load. We have also obtained our vertical load at the wall base. In the next class, we will look for compliance of our wall to various material and wall geometry specifications for earthquake resistance. Thank you.